Hello everyone, today I'm gonna present a video explaining an exercise using Lagrangian mechanics, and as well as we can understand where I use the coordinates to have a very useful solving Lagrangian equation problem. Well, this is my trick where it's so useful for me. For example, what I mean, like for the coordinates, because imagine that we have a block and a sliding triangle block, for example, and you know that if that block slide in that way, this triangular block gonna go in that way. So for that, we know that it's very stressful, like take x and y coordinates for this block. So someone use like s and x in that direction, right? So the question is how was the understanding of use that coordinates? So for that, I bring to you like this problem that represents very well what I'm trying to teach you. So how can I use the coordinates? Well, I use vector loop. That is very useful for me to understand, right? The equations and where I saw vector loop in theory of machinery. Okay, it's very simple. It's just vectors, and it says like the sum of the vectors needs to be 0. So knowing that, we can represent like this mass that goes in that place, okay, in that street, in that wall. So the question is where I take the vector loop. So for machines, it's very easy to take like enough inertial frame where you can see like the movement very easily through the vector. For example, if you have a slider crank, right, it's gonna be like very difficult to stand up right here and see like this vector and this vector, because it's like, okay, if I move in that way, I know that this is very shortly, but it's like kind of difficult to understand what is happening standing right here. So the inertial frame is more easy to take this inertial frame and understand that if that vector go in that way, that if that slider goes in that way, that vector gonna grow up. Okay, so knowing that, I know that if I stand right here, I can know that if this move in that way, this gonna go up. So this vector gonna grow up and this vector gonna like make more little, because I see that it goes inward to me, right? And well, also it's very useful to take like angles from the x frame axis and understand what is happening. But in that case, we have theta, and we have to express all the problem from the equilibrium position in function of theta. So how can we do that? Well, it's easy. I'm just gonna take this vector, because I know that if this theta is like minus theta in function of this frame, it will be very easy to understand what is happening. So I take this vector that R1 plus R3 is equal to R2. So for me, that's very easy. Okay, knowing that R1 we can express this in complex numbers. Knowing that R1 vector is the magnitude at R1 Euler 180 degrees, right? And R3 is R3 minus theta degrees, and thus is equal to R2 Euler minus 90 degrees. Well, knowing that, we can express these complex numbers in R2 because they are like isomorphic, something like that. Okay, so if we express this like, cosine, we have Euler to theta, j, you're gonna express like cosine theta and sine of theta. So I do that. I put like R1 cosine of 180, and that's minus 1 and 0. And I do the same stuff for x and y. Okay? So, also, I can express this equation. And now, as you can see, I can express also that x is equals to R1, and that is equals to minus L cosine of theta. And the same with y. R2 is equal to L sine of theta. Right? Well, we take the derivative to take the velocities, and we know that R1 is changing. So we take the R1 derivative, R1 dot. The angle is the same because it doesn't gonna change. And L and theta, and well, what happened here, I take the derivative of theta because R3 is L, right, the modulus. And if I take the derivative, I also shift the angle 90 degrees. For like the complex number, the matrix of rotation, right? And we take the same stuff we are to. We express in the matrices, and we know that x dot is equal to L theta dot sine theta, and y dot is equal to minus L theta cosine theta. Okay, we have that stuff. And right now we have to represent the kinetic and the potential energy. So the kinetic energy is very easy because it's 1/2 of the inertia plus, times theta dot to the square, right? The potential energy from a rigid body, And the potential energy is like kind of different because we have two hooks and the potential gravity. So we take like 1/2 K1 times, and that is very, very like useful. That what I'm gonna say. Not is x squared. That's a problem because I used to do that. The real solution that says in the book, in the physics book, in the simple physics mechanics books, is the differential of position to the square. And that's very, very, very different to solve all that kind of problems. Why? Because we have to understand where was the initial position and where it's gonna be the final position. For example, in that stuff, it start on a stretch like horizontal, and that's very important because we have like right here the hook, and then like right here we have like another hook. So something that is gonna happen, that's its initial position, well, that's my frame, my initial position gonna be L, and my final position gonna be minus L cosine, right? L cosine, right? So that's very important. So knowing that, we can express like the states that I'm gonna show you that it's gonna be, well, let me write it like right here, the differential that is very important. They're gonna be L cosine of theta minus L, because L is initial position, and that to the square. Okay? Also, we have minus 1/2 K2. And well, where's the initial position and difference? Is different to that? Well, not, because it's gonna just move in that way. From that inertial frame is like 0 to the initial position is 0 for y, right? So just gonna be L sine theta, right? And then is plus, well, yes, plus mg, right? The high. And where is the high? Well, we have the high. The high is L sine theta. Okay. That's very easy. I express all the coordinates in function of theta. So I don't know if well, the minus sign obviously is for the reason that always the hook is pushing back, like wherever you goes, and the potential energy depends on the frame. So initially I expressed that this is my frame, so I just put like plus mg, and that depends on g, okay, on the high. But I also confused that this is in the center of mass, that is like right here, L and a half, right? Okay. Well, right now we can express the Lagrangian mechanics. The Lagrangian, we can express the Lagrangian, that is t minus b. So I want to have 1/2, or the inertia from theta dot square minus, so that makes minus minus, right? So that's gonna be like plus 1/2 k1. Well, I can take like, right? I can take it like this, minus 1 square, and then I have plus 1/2 k2 L square sine square theta, and then I have minus mg L and a half sine of theta. Okay. What is the next step? Next step is express like the equation of the Lagrangian mechanics, that is the derivative of sine of q dot minus derivative of the Lagrangian q equals to 0, right? So if we know that, we can understand that first we wanna take that in function of theta, right? So there is no theta, there's a theta, there is a theta, and there is a theta. So I can take like 1/2 k1 L square, and what is the derivative of that? Well, the derivative of that is, well, no, is minus 2 sine of theta times, okay, and then the next one is k2 L square, and that is 2 cosine of theta sine of theta, and finally I have minus mg and a half and cosine of theta. This is very easy, right? So I have that, and I also have to express this like what cancels, that cancels, and well, there is this expression, and another derivative is theta dot, and just appears right here. So I got like ag theta dot. Okay, well, with that I can show you that we have to take the derivative of time, and I got the inertia theta double dot. Okay, right now we have to make negative that part and added this. So finally I got the Lagrangian mechanic equation. They're gonna be theta double dot minus k1 L square sine of theta plus cosine of theta minus 1 minus k2 L square cosine of theta sine of theta plus I almost confused plus let me see, plus mg L and a half cosine of theta equals to 0. Okay, that's for me the solution of this problem. And you can take like, you can use it like vibrations, making those stuff like approach to 0, how it vibrates, that kind of stuff. But my video not ends right here. I also brings you a code I also bring you a code where you can see the Lagrangian, right? Good, paste. Let me paste right here. Okay. I want to show you what happened. Well, this is my code where I express like the function of the Lagrangian. What is the Lagrangian? It's like to find the minimum points where it's more stable. So, as we know, when theta is 0 and omega obviously is 0, okay, you're gonna go downward like this and reaching that point, that brightness point, when all M, L, K1 and K2 are 1. But what happened if I change the rigidity of, or the stiffness of K2 like this? Like this, when its position is more stronger, okay? When this is more stronger, you're gonna like bring back this link downward. But also, when this goes so downward, you're gonna go upward, like jumping. And as we can see, if I change K2, the hook 2, you can see what happened. It stabilized like in theta equals to 1, not equals to 1.5. Like it moved in that way. So what it means that like in this situation, the stabilizing point is gonna be something like this, right? But in that, it's gonna be something like this. Okay, it's like it very rich, a very near condition to that, because obviously it's gonna fall down. But in that case, when this is stronger, like it moves to that position. So it's like it's something that can help you understand the Lagrangian mechanics. It's like through a ball in that hill and gonna goes downward. Okay, I'm gonna like the video, give me a like and subscribe. Thank you.